Alright guys, today we're talking about perimeter and area, but not just like we did before, but of similar figures. So we need to finish our title out. I kind of cut it short. Perimeter and area of similar figures. We've talked about similar figures before, mostly in triangles and comparing ratios of side lengths and such. Now we're looking at, we're going to be comparing the ratios of perimeter and the ratios of area. I've put these out in color so that you can understand the ratios, how I have them listed here. The ratio of perimeter, you just put the entire perimeter over the entire perimeter of the other one, and you can reduce it. However, basically it's the same thing as just writing down one side length and comparing it to a corresponding side length of the other one. I'll show you what I mean. We're comparing red to blue, so we're going from the bigger object to the smaller object. And you can do it either way. Sometimes it asks to specify and compare from one to the other, and so you want to be sure, however it asks you to list it, that's what goes on the top. Okay, so if we were to look at this figure right here, this one has a perimeter of 10. 3 plus 2 is 5, plus another 5 is 10, and that's how we get this number right here. The red one, we've got a side of 6 and a side of 9, so we have 9 plus 6, which is 15, and then another 15, which is 30. So if we're going to write this as a ratio of red to blue, our perimeter is going to be 30 to 10, which reduces down to 3. Now, if I want to use that with just one of my sides, I would pick corresponding sides. So this one has a length of 3, this one has a length of 9. If we're doing red to blue, then we would have 9 to 3, and 9 to 3 reduces down to 3 as well. If we were to use the other sides, 6 and 2, 6 to 2, it also reduces down to 3. And the reason why that works is because perimeter is one-dimensional. You're finding the length, and length is always one-dimensional. And so it'll work for whenever you're using perimeter, writing your ratios of perimeter. Area is different. Area is two-dimensional. It's two directions. All right. So here, how we get our area, of course, is base times height. So 2 times 3 is 6. That's our blue area. 6 times 9 is 54. That's our red area. And when we reduce that down, we get an answer of 9. Okay. Now, we said that area is two-dimensional. So another way you can write this would be like this. The side squared compared to the side squared. What that means is I am going red to blue, so we're going to continue with that. Let's note this is perimeter, and this is going to be area right here. So if I wanted to compare my ratios of area, I could take one side, which is 9, and square it and compare it to my other side, which is 3. These are corresponding sides. And then that would be 81 to 9. Well, what does 81 divided by 9 equal? But 9. And that is the same answer as we got up here when we compared their actual areas. The actual areas are two-dimensional. So if you were to take a one-dimensional length, square it, now you've made it two-dimensional. All right, and then you can compare it that way. If you were to use your other sides, 2 and 6, we would have 6 squared over 2 squared, which would be 36 to 4. And 36 divided by 4 is 9. All right, so if the ratio of your perimeters is A to B, and that's just in generic form where you take the length of your sides and compare them, then the ratio of the areas are the same numbers except they're squared. So it's really easy to find those ratios, and you don't even have to know the area of the figures, and you can still write a ratio comparing the areas. All right, now we're going to kind of compare these. So if we have two figures, doesn't matter what the figures are, but their corresponding side lengths are 6 to 11, well then our ratio of perimeters is going to be the same. This is one-dimensional, this is one-dimensional, and we can write that down. 1 dimensional, 1 dimensional. So our ratio is going to be exactly the same, 6 to 11. However, dimensional, so let's write that down, 2D, 2-dimensional. So what we're going to do is we're going to square the 6 and the 11. 6 squared to 11 squared. Like I said, I have no idea what the area is of these two. 6 squared, which is 36, and 11 squared, which is 121. All right, you always want to simplify. You always put them in simplest form. This does not reduce down. It stays 36 to 121 because we already had it reduced. 6 and 11 can't reduce any further, so when we square it, it won't be able to reduce either. Now, here we got our ratio of perimeters. Well, our ratio of perimeters right here, that can be reduced down. So when we write our ratio of corresponding side lengths, we're going to take this number and we're just going to reduce it. So 20 and 36 both have a common factor of 4. So 20 divided by 4 is 5, and 36 divided by 4 is 9. So our side lengths are 5 to 9. And keep in mind that we would want to reduce this down as well. So I'm going to go ahead and put 5 to 9. This might be the actual perimeter and the actual the actual perimeter of each figure. Now, when we do the ratio of areas, what do? We square those one-dimensional lengths. So we would have 25 to 81. And again, those are simplified because 5 and 9 cannot reduce down any further. Now I'm writing it with the colon. Remember, there's several ways to write a ratio. You can write it as a colon. You can use the word 2, 5 to 9, or you can write it as a fraction, 5 over 9. These are all have the same meaning. It's just comparing the two numbers. Now, find the ratio of the perimeter and area of these two figures. Keep in mind, you do not have to know the actual perimeter of a figure to write a ratio for its perimeter, nor do you actually have to know the area to write a ratio. So what we're doing here is these are similar figures, similar triangles, and we have corresponding sides. One is 2 feet and the other is 6 feet. And it does go ahead and say that the area of the smaller triangle is 2 feet squared. Well, if I'm going to write a ratio of the perimeter, okay, that's one-dimensional. So, and it doesn't say which triangle to put first. It didn't say from big to small or small to big. One's not shaded to go from shaded to unshaded. So what I'm going to do, let's go ahead and let's go from the small triangle to large triangle. That's going to be how we write our ratio. And since I said small triangle first, that number comes first in the ratio. Okay, so my side length is 2. My side length here is 6, and 2 6 reduces down to 1/3. So our ratio for our perimeter is 1 to 3. So in other words, this one is 3 times greater than our other one. Or the perimeter of this is 1/3 the length of the bigger one. Now if we're going to write a ratio of area, okay, now we know that the side is 2, and this side is 6, and remember we take those one-dimensional lengths and we square them. So 2 squared is 4, and 6 squared is 36. Now, 2 6 is not reduced down in simplest form if we had left it like this. So therefore when we square it, it's still not in simplest form. It can be reduced down further. So we would reduce this down to 1/9, and this is our ratio of our areas. Now notice 1 to 3 and 1 to 9. Notice that this bottom number is squared to get this one. That's because this one's two-dimensional. So if we were to compare our areas, this area is 1/9 the size of this one. In other words, it takes 9 of these to fill up this one. Or this one is 9 times as great as this one over here. Now, these are not drawn to scale, so it's probably hard to visualize that in there, but keep that in mind. This is a very common tax question that is missed over and over and over again. That when you increase area, when you are comparing area, your dimensions are squared. So we're going to be practicing that on the homework. The notes are short and sweet. There you go. And I'll talk to you guys later.